Hi everyone. In today's video, I'm gonna walk you through a fundamental skill in material synthesis, which is how to calculate the amount of reagents you need to make a perovskite oxide. Later on, we are gonna proceed to the lab and I'm gonna show you step-by-step process to synthesize a typical perovskite oxide material using the sol gel method. So let's get started. Step 1, we have to have a target composition. In this case, it is barium, zirconium, yttrium, zinc, oxide. And the molar ratio of each cation is barium, which is the A-side cation, it is 1 because it is the only A-side cation. And the B-side cations are zirconium, yttrium, and zinc. And the molar ratio is 0.8, 0.18, and 0.02. The next step is to select our precursors. Your precursors, they can be nitrate or acetate, and when you do not have, let's say, the nitrate or the acetate of any of these materials or precursors, you can use an oxide, as we are going to show in this case. For the first, we have barium nitrate. For the barium nitrate, we have the molar mass to be 261.35 gram per mole. For zirconium, when you calculate the molar mass, it is going to give you 270.83 based on the precursor we have. And for zinc, the same thing. And for yttrium oxide, you have that too. Now, I'm going to show you a website where you can quickly achieve that, which is chemicalaid.com. You just simply paste the formula or the chemical molecular formula. So once you paste it, just click on calculate. And once you click on calculate, you're going to have the approximate molecular weight of barium nitrate. So that's it. You can do the same for other precursors that you have. Now you can see how you can calculate the molar mass or molecular weight for each of the precursors. For the yttrium oxide, each mole of yttrium oxide, it provides 2 moles of yttrium ion, but we need just 1. So you divide it by 2 and that will give you 119.05 gram per mole. Now the next step will be the general formula for reagent calculation, which is the mass of the precursor needed equals the number of moles of precursors required multiplied by the molar mass of the precursor. To calculate the number of moles of precursor required, the formula is simply the stoichiometric coefficient of the cation in each of the formula. In the formula you have multiplied by the target moles of perovskite units. Now the next step is the target batch size. Supposing we want 2.76 gram of the material, which is BZYZ. This is an abbreviation for the chemical formula. So we will calculate the molar mass. You can go back using the website I provided earlier. The molar mass is going to be 275.62, and once you have that, the target moles of BZYZ, which is N, will be the amount of or the gram you want for the total material divided by the molar mass, and that will give you 0.01 mole. Now once you get the 0.01 mole, you proceed to the next step, which is the moles of each cation. Now for each of the cation, now you know the molar ratio to be 1. Now you multiply it by the number of moles for the total material, which I showed you in the previous slide from here. Now you multiply each of the molar ratio by the number of moles, and that will give you 0.01, 0.008, 0.0018, and 0.002. Now you proceed to convert to the precursor mass. Now for the first, which we have the barium nitrate, and we have the molar mass. Now you will multiply the moles by the molar mass, and that will give you the exact amount of reagents you're going to weigh for your synthesis. Same thing for zirconium. Now you have the molecular weight by the number of moles, and then you have the exact amount of mass. The same thing for the yttrium oxide, which we mentioned. You're just going to multiply that from the slide, 0.002 mole. You multiply that by the molecular weight, and then you get the exact amount of gram you need to weigh in your beaker for synthesis. Now the next is chelating agent. You see, chelating agents, they are very important. We often use them during synthesis, and typically we use EDTA and citric acid for the sol gel method. When you calculate the molecular mass or the molar mass, molecular weight or molar mass, you're going to have it to be 292.24. This is for citric acid monohydrate, and you will have the molar mass to be 210.14 gram per mole. And the ratio of ADTA to citric acid is typically 1:1.5. It could be 1:2, depending if you want. You can use 1:2, there's no problem with that. The total number of metal ions, you can calculate that by just simply adding up all this molar ratio, and that is 2. We have 2 metal ion. Now, to know the amount of ADTA you're going to weigh for your synthesis, it is simply the molecular weight multiplied by total number of metal ions multiplied by the ratio here, which is 1, multiplied by the number of moles. The same thing for citric acid, the molecular weight multiplied by number of metal ion multiplied by 1.5, the ratio here multiplied by the molar concentration. Once you're done with that, then we're going to proceed to the lab, and this is exactly what we're going to do in the lab. You're going to dissolve the nitrates, weighing the amount of reagents which we calculated. You weigh the nitrate for barium, zirconium, and zinc in deionized water. The second is you're going to dissolve yttrium oxide in nitric acid so that you can convert it into a soluble nitrate. The next will be to dissolve ADTA and citric acid in deionized water. Then you mix all the 3 solutions together in one beaker after they have mixed reasonably under heating and stirring condition, and then you will use ammonium hydroxide to adjust the pH to around 7 to 9, and then you subject it to the heating and stirring, and evaporation of the solution will occur. You're going to get a gel, and after a gel you get combustion. Then you will collect the powder and calcinate the material using a aluminum crucible at around 1000 degrees Celsius, and you will get your final perovskite oxide material. Let's get started. We're going to proceed to the lab now to show you exactly how it's been done. So here is barium nitrates. We are weighing 2.6135. Okay, so approximately 2.6135. We can go with this amount just approximately to save our time. So that's it. We weigh it into an empty beaker so that we can use. So that's for barium. The next is zirconium. Here's our zirconium dinitrate. Zirconium dinitrate. We're going to be weighing 2.167. Alright, so approximately 2.17 should do. Okay, but try to minimize it as much as you can to be close to the actual value, because it's 2.1666. Okay, let me try to take out 1 grain. Alright, that's about it. Okay, so that's it, 2.166. We pour that into the beaker. The next should be our yttrium, but we're going to leave it separate first. We go to the zinc nitrate. So we have the zinc nitrate here. That will be 0.0, approximately 0.06. Okay. Oh yeah. So that's about it. About 0.06. So we transfer that into our beaker approximately. Now for the white trim, we're gonna be using a separate beaker because we're gonna be dissolving it in acid. And the amount we're weighing is gonna be 0.2, 0.2. So we have our white trim in a separate beaker. It is better if we also dissolve our EDTA and citric acid in another beaker because we're going to be using ammonium hydroxide to monitor the pH until it's about 7, 7 to 8. So let's weigh the EDTA and citric acid. Our EDTA is about 5.844. Okay, so that's an approximate value for EDTA. The next is our citric acid. It will be 6.3042. It's about 6.3. Okay, so let's go with that. Now the next thing we do is to insert our magnetic stir bar into each of them. One. The next, we're gonna add deionized water. After this, we're then gonna transfer them to the fume cupboard where we have the heater and stirrer, and then we'll wait for everything to dissolve. So we are going to maintain this until we have everything dissolved. This contains our EDTA and citric acid, and the other contains other reagent. Meanwhile, for the white trim, we are going to be dissolving that in an acid, and once it turns clear, then we are going to transfer it into the remaining reagents so that they can all mix together. Make sure to close the shash. There we have our white trim oxide mixing in acid. We are actually using nitric acid, which is about 70% pure in water. Make sure you exercise serious caution when adding your acid to the white trim oxide. You need to exercise serious caution, so you add it in the fume cupboard. So we try to mix them together now. We mix in the citric acid and EDTA mixture together with the other reagents. Then we will check our yttrium oxide if it has successfully dissolved in acid, and then we are going to mix everything together and then use ammonium hydroxide to control the pH of the entire mixture. To return that to our magnetic heater and stirrer. Now we can see that the solution of yttrium oxide in acid is clear, which gives us the signal to transfer it to the other reagents, so that we can balance the pH back to around 7 to 8. You can see it's clear. So we're going to transfer this into the other mixture and continue eating and stirring. And then we're going to add ammonium hydroxide to control the pH. Thereafter, we're going to leave the whole thing to dry until combustion takes place before we can proceed to the calcination stage. Now, back here, we have the clear mixture of the yttrium oxide in acid and nitric acid, and then we're going to transfer it into our existing solution. So after doing this, the next thing will be to add ammonium hydroxide to continue monitoring the pH until we have a pH of about 7 to 8. To achieve that, we're going to be using litmus paper. So here's our pH scale. So when you have this color, after dipping the litmus paper into the solution, then you can tell the range of the pH. Once it's between 7, 8, 9, then you know it's okay. So now I'm gonna pour in some ammonium hydroxide and monitor the pH until it's within the range I just mentioned. Normally, as we continue to add ammonium hydroxide, the color of the solution should change. It should become clearer because it is going to prompt the dissolution of the citric acid and the EDTA. Now we've added some amount of ammonium hydroxide. Let's try to see what the pH will be. So you can see we still need more ammonium hydroxide because the color hasn't changed. Now let's try to add more ammonium hydroxide. As I added more ammonium hydroxide, the color systematically changed. So the whole solution appears to be pure, which is a good sign. It means that we have achieved a good mixture. Now we're going to verify that by checking the pH again to confirm if truly the pH is within range and we have a reasonable mixture. Absolutely nice. So we can see the color of the litmus paper has changed, and that shows that it's within range. The pH is now currently close to about 9, which is within range, acceptable limits. Now we are going to wait for the water to dry and for combustion to take place. So we will continue waiting for the next couple of hours until it dries, becomes a gel, and then combustion takes place. I understand that I mentioned that this is sol gel method. At the same time, I've been saying combustion. The reason I mentioned combustion is because in this method we used nitric acid to dissolve the yttrium oxide. So because of that, it's a modified EDTA approach. When you do not have yttrium nitrate, you can go through this route. And through this route, we're gonna obtain final particles, as you will see at the end of the day. So we're just gonna wait for this to dry. Once it dries and combustion occurs, then we're gonna collect the dark or black char, and we are then going to calcinate the mixture. After the calcination, we are gonna see the end result together, which will take maybe about 1 day or thereabout. So let's wait for this solution to dry so that we can capture the time it ignites and the combustion takes place. See you later. It's about 2 hours now, and we can see that the solution or the mixture is drying. We're making good progress. We're just gonna keep waiting and wait until the combustion occurs. Exciting. We can see the color has changed. Things are drying up already. The mixture is drying and things are proceeding smoothly. In a couple of minutes or about 30 or 1 hour, combustion should take place, and we should be able to collect our fine dried particles that we are going to then calcinate in the furnace. Now the next phase is to collect everything into a ceramic crucible so that we can proceed to calcinate the material. So we just gently and carefully collect them. Right now, we are proceeding to the calcination stage. So we are gonna calcinate this material or this mixture at a temperature of 1000 degrees Celsius. So there you go, our sample is out. You can see the powders very clear, white. All the dark particles have changed, all metamorphosed into white substances. There is our powder, very fluffy. So with this, we can use this to prepare membrane, or in the preparation of our cells for ceramic electrochemical cells, or for membrane for other applications. So there you go, that's the end of our video or illustration on how to synthesize particles or materials or perovskite for various applications. If you have any specific questions, drop it down in the comments. Don't forget to like and subscribe.